for you, but if I don't reschedule this class means we'll not be able to finish the syllabus. Okay, so because next Tuesday is also holiday, so next Tuesday is also we are not having any class. So let's start today's lecture. So first I'll give you an example. Solve the differential equation. Differential equation using Laplace transforms. So for Laplace transform, I'm writing in short form LT. Question is y double dash plus 2y is equals to 4t e power minus 2t. And initial condition is given as y0 is equals to minus 3. So if it is first order differential equation, only one initial condition will be given to you, because you will get only one constant and that you can find using this. So solution. See, if we take Laplace transform of both the sides, so Laplace transform of y dash plus 2 into Laplace transformation of y, 4 into Laplace transformation of t e power minus 2t. Okay, so this we need to find separately, or you can write down, but it's okay, we'll find here. See, if you remember that Laplace transform of t ft, I have written many formulas, right? T and ft is equals to minus f dash s, where fs is nothing but Laplace transformation of ft, right? So if you know that Laplace transformation of ft and this ft is multiplied by t, any power of t, then minus f dash s. Or even we have written the general formula also. If I'll recall that this is t power n ft is equals to minus 1 power n nth derivative with respect to s of this fs. Okay, so this is when ft is multiplied by powers of t. See, now we know ft. So here, if I'll compare with this, ft is e power minus 2t, right? And we know that fs is nothing but Laplace transformation of ft. Okay, so Laplace transformation of ft is this e power minus at, or you can say e power at is 1 by s minus a. So if it is minus, you will get plus here. So 1 over s plus 2. So this is your fs. Now this is multiplied by t ft. Now it's Laplace transformation. That means derivative of this minus d by ds of 1 over s plus 2, right? So s plus 2 power minus 1, you know, right? And minus minus plus 1. That means 1 over s plus 2 whole square. So this RHS I have solved here. Even once you solve, you can directly write this 4 over s plus 2 whole square. That means if you have any powers of means, now okay, let's proceed further. This is nothing but s into Laplace transformation of y minus y0. If you remember the formula of derivative of function, 2 into Laplace transformation of y. So we'll collect the coefficient, this one and this one. That means s plus 2 Laplace transformation of y, and this is minus y dash minus y0. So minus minus plus 3, that means 4 s plus 2 whole square. You will get here minus 3, right? So Laplace transformation, I'll write here, Laplace transformation of y is nothing but 4 over s plus t whole cube, right? Minus 3 over s plus 2. So you need a value of y, that means Laplace inverse of 4 1 by s plus 2 whole cube and 3 into Laplace inverse transformation of 1 over s plus 2. Now see, if Laplace transformation of this is 1 over s plus 2 square, so you should get to know by seeing the form, like it is something like in the function, initial function, it is multiplied by some power of t, right? When ft is some exponential function, and when ft is exponential function and it is multiplied by power t, like if it is t power 1. Okay, so please understand here. I'll erase this. See, if I write this tft, right? tft is goes to nothing but L inverse, or you can take minus this side, L inverse of d by ds of this fs, right? Or you can say that L inverse of 1 over s plus 2 whole square. So it will be plus. So this is TFT. TFT value is L inverse 1 over s plus 2 whole square. Right? From here I am writing only. Now if it is 1 over s plus 2 whole square and we have used here and it is multiplied by t and it is s plus 2 whole cube, that means it would have multiplied by t power 3. Sorry, t square. Okay, so if I write here, I will erase and I'll write here like so. Where should I erase? Okay, let's erase from here. So please, now this, I think you have noted it down, so I'm erasing. Now we need 1 over s plus 2 whole cube, right? So if I'll simply take d2 over ds square of 1 over s plus 2, because it was only the first time derivative, right? Here d by ds. So let's take, because now if we'll multiply by power 2, so it will be square. Then only you will get, see, if it is first order derivative, you are getting power 2. If it is second order derivative, surely you will get power 3. So let us see what it is. So first time derivative is minus 1 over s plus 2 square. Second time derivative is minus minus plus 1 and even 2 and 1 over s plus 2 whole cube. So this is d2 over ds square of this. That means in place of this, or you can say that this is nothing but d2 over ds square 1 over s plus 2. We need this value, right? So in place of 1 over s plus 2, I can write 1 by 2, right? So here write this 4 by 2 L inverse of d2 over ds square. This is same, right? It will be balanced. If I'll just simply take second order derivative of this, you will get the above term. And wait. So this and this minus, simply you can write 3 into e power minus 2t. Now this is nothing but second order derivative, right? So second order derivative means it would have multiplied. If I write the formula again, this Laplace transformation of t square ft, t square ft, this is Laplace transformation, is nothing but positive value, because minus 1 power 2 and d2 over ds square of 1 over fs. right? Now it is minus 1 power 2 means positive value. That means t square ft is nothing but L inverse, Laplace inverse of d2 over ds square fs. Okay, now here the same d2 over ds square fs. Okay, so I'm writing here. So t square is here. Now this value 4 by 2 means 2. We need t square. Okay, write t square. But what is ft? Ft is nothing but the corresponding 1 over s plus 2. 1 over s plus 2 means ft is nothing but L inverse of fs. And fs was 1 over s plus 2, right? This is fs 1 over s plus 2. Simply it's not square, 1 over s plus 2. That means e power minus 2t. This is ft. So e power minus 2t. So first term is 2 into t square e power minus 2t and minus 3 into e power minus 2t. So this is your answer. That means to solve these type of equations, you should know the Laplace transform and inverse Laplace transforms. Like how to use these to find the inverse Laplace transforms. Okay. So here we do not need any partial fraction because it is already in the partial fraction form. Just I want to give an example when it is multiplied by t. So better you you just go through the Laplace transforms, some questions, or if you want, I will write some questions for you. Even I have written for the morning session also. Those documents where I have written group course. Today I was having class. That's it. I was having class 8 o'clock. Okay. 8 o'clock. Nothing is there. Where is morning session class? Okay, no problem. So next we are going to discuss unit step function or Heaviside function. That is important. Unit step function or Heaviside function will be given to you in your RHS of this type of differential equation, and it is separately mentioned in your syllabus. That means an important topic. So please note it down carefully. Everything I'm writing from the B.S. Grewal book related to this. So you can go through that. Unit step function. Or another name is Heaviside function. Okay, so unit step function is defined. It is defined as u of t minus a. This is unit step function denoted by u of t minus a. There is a lot of means two more notations for this. So its value is 0 if this t, you can say that if t is less than a. So whenever this t is less than a, its value is 0. And if t is greater than a, its value is 1. Okay, where a is any positive value. So by the graph itself, suppose here it is the graph and this t and the unit step function t minus a. On x-axis it is t, on y-axis it is the function, right? Now suppose here is a somewhere. Okay, so if t is less than a, so its value is 0. 0 means this up to here. For this value of t, graph is this. But when t is greater than a, now a is not included in that. So this line, so it is not included. This point is not included. Just it is near to that. This, its value is 1. Suppose 1 is somewhere here. Okay, so 1, this point, this function is not included here. So this is the graph. This. Now by the graph itself, unit step function. So it is taking a unit step. Okay, so unit step function or Heaviside function. Another rotations are u of t and in a suffix a. Another notation is h of t minus a. Heaviside function or unit step function. So you can see in any form it may be given to you in like any function. Any notation can be given to you. So please remember, notations means this only. Now suppose if this a is 0, then unit step function is u of t, right? If it a is 0, u of t or h of t or simply u naught of t will be defined as 0 if t is greater than 0 and 1 if t is t is less than 0 and 1 if t is greater than 0. And graph simply this, not included this but near to this, like that. Okay, so here it is t, here it is unit step function. You can say u naught of t. So this graph, like it is either it is 0 or it is giving 1. Now this is unit step function. So what is its application? Using unit step function, we can write any function which is piecewise continuous function in the addition form of its components. Okay, so this is the use of unit step function. Now suppose if you are multiplying unit step function with any function given ft. So in the next page I'll tell you the product function. See, when we multiplied unit step function with any function of t, like this ft and u of t minus a, takes values. So u of t minus a, only two possibilities, either 0, either 1, right? So ft u of t minus a. So simply I'll write, if u of t minus a means if t is less than a, its value is 0. 0, and if it is multiplied by ft, so again it will be 0. See, if it is multiplied by ft dot 0, that means you will get 0 only. So instead of this, simply write 0. And if t is greater than a, its value is 1 and ft is multiplied, so f of t, you can say f of t. So when a function is multiplied from by if any function is multiplied by unit step function or Heaviside function, this it will be defined by this. That means, so the function, which function? This Heaviside function, you can say u of t minus a may be interpreted as a device for switching on the function ft. So its real life example is when we switch off any plug. Okay, you can see that if you are switching on, immediately you will have the light or anything, and if you are switching off, immediately it will be 0. Okay, so that is the real life example of unit step function. So any function, like if it is in current form or this is multiplied by unit step function, then only it is immediate action we are getting, either 0, either 1. So either 0 or it may be the current. Okay, so that is the real life example of this. In this way, the unit step function may be used to write a concise formulation of piecewise continuous function. Okay, so that we discuss later how to write. Now, let us define u of t minus a. You already know, right? 0 when t is less than a and 1 when t is greater than a. Let us take another b. Its value is again 0 when t is greater than b, less than b, and its value is 1 when t is greater than b. And let us see a is less than equal to b. A is less than equal to b. Then what would be the u of t minus a minus u of t minus b? Means the subtraction of two Heaviside function defined on the different points. And these different points means one can be greater than another one. Okay, so u of t minus a. So first, if you are noting this, simply I'll make a small graph here for this. See, a is here, right? And this is on t, so you will get this, right? This unit step function, this. And for this x-axis, y-axis, if a is here and b is greater than, so this. That means for this function, this is the graph. So this is the graph for this, and if b is here, this is the graph for second function, this. So when you are subtracting this, from the graph theory, you will have only up to here, right? Up to here, the subtraction graph. So if this is a and this is b, not included that, so it is this graph, just this graph. See, Heaviside function, u of t minus a minus u of t minus b. So when we have two Heaviside function and we are seeking the graph of their subtraction, then you will get this only. Okay, so where this is t and this is the resultant function. So how to write this form? Like 0, or because we have one value, so first write 1. See, 1 value is 1 when t lies between a to b, right? So 1 if t lying between a to b. Now 0 otherwise. So this is the subtraction of two Heaviside function, 1 or 0. Means if it is t minus a and t minus b, two values are given, then if t lies between a and b, so its value will be 1, and for any other value of t, it will be 0. See here, it is 0, here, 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 everywhere it is 0. Only for this, when t lying between a to b, its value is 1. So that you need to remember. Using this property, we'll be able to define the piecewise continuous function. How? Okay, so we'll see that function only. Suppose a graph of function is given. Piecewise continuous function graph. You already know what the piecewise continuous function. Suppose 0, then at t1 interval, at t2 interval, up to t2 and so on. So up to here, function is defined by this. Suppose f1t. Piecewise continuous, right? Now it is defined by f2t. Now from t2, it is a constant function like this, f3t. Okay, so how to write this complete function? Ft is what? When t lies between 0 to t1, its value is f1t. Right? When f to t when t lies between t1 to t2. Or even you cannot, if you wish, you are not including, that's fine, because it's already included here. And f3t for t greater than equal to t2, right? So this function is given. So using Heaviside function, we can write this type of piecewise continuous function in the addition of their components. So how to write? See, ft. If I'll take f1t, and when t lying between 0 to t1, I can write the Heaviside function, right? U of t minus 0 minus u of t minus 1, like from the previous one. If it is lying between a to b, a to b. So u of t minus a minus u of t minus b. Okay. So u of t minus 0 minus u of t minus t1. Right. Now complete for this. Then u of t minus t1 minus u of t minus t2. This is f3t. This is value means u of t minus 1 and u of t minus 2. That means its value is 1, right? Its value is 1. If t lying between 0 to t1, its value is 1, its value is 1. Okay, so you can write now f3t. You can simply take t2 this side, means I'll just to make you understand, t is nothing but like t2, and here term is not given, so simply you can write u of t minus t2. Okay, now f1t, this so you can you have written any function which was given the piecewise continuous function in the addition of its components using Heaviside function. So this is the application of Heaviside function. Any function, but it should be the piecewise continuous function, can be written in the addition of their components. So how to write? U of t minus 0, no of u of t minus 0. Okay, so f1t is u of t plus f2t for this one, f2t u of t minus 1 minus f1t. So u of t minus t. Similarly, f3t minus f2t will be multiplied by u of t minus t2. So this is your ft. Any doubt in this? Any doubt? So is anybody listening?
No doubt, ma'am.
No, ma'am.
Okay. So just for 2 minutes, one little concepts also.
No, ma'am.
What, no ma'am? No doubts. Now, because we are studying this Laplace transform, so Laplace transform of unit step function, or you can say that Heaviside function. Very simple it is. Laplace transformation of u of t minus a, right? And you know that how to define u of t minus a. Its value is 0 if t is less than a, and its value is 1 if t is greater than a, right? So Laplace transformation, if you do not know the direct formula, use the definition 0 to infinity e power minus st ft dt. Ft is u of t minus a. But you know, we have the point 0 to infinity, we have the point A. So let us take 0 to A, right? But 0 to A, if A is here, functional value is not given. At t is equals to A, function value is not given, right? So function is 0. That means its value is 0 between 0 to A. So e power minus st into 0 into dt. Now A to infinity. So A to infinity, function value is given as 1 dt. So this is completely 0. That means we need to find this. A to infinity e power minus st dt. So e power minus st divided by minus s. Okay. Now limits A to infinity. So upper limit t tending to infinity e power minus st minus lower limit, that means e power minus at. No, e power minus st, we are substituting for t. So in place of t only we need to write, that means as. Okay, so when t tends to infinity, its value is 0. So directly write 0. So it is 0, it is this, that means e power minus as by s. Laplace transformation of u of t minus a is this. And this is very important. Okay, so please remember this formula whenever, means if you want to find Laplace transformation of u of t minus 2, directly write e power minus 2s divided by s. That's it. Okay, so this was the Heaviside function. When we were discussing the second shifting property, right, we came to know to this u of t minus 2. Then I have said that we'll discuss this Heaviside function later. So now everything I have discussed related to Heaviside function. So in the next class, we'll discuss examples or differential equations which contains Heaviside function in RHS, and then how to solve. Okay, so today class finish. So only 35 students has joined. Thanks for joining. I'm taking attendance. Please mark your attendance, everybody. And those who have marked their attendance,